About 2 billion years ago, marine organisms, algae, and microscopic animals and plants died and settled on the ocean floor. Beneath other settlements in the ocean and in the absence of oxygen, these fossils change into a substance called kerogen, and the heat and pressure kerogen gradually changes into oil or gas. The whole process usually takes at least 1 million years. At the molecular level, oil and gas are hydrocarbons made up of hydrogen and carbon atoms. The constant pressure and movements of the Earth's crust squeezes oil and gas through the pores or spaces within rocks. Some oil and gas reaches the Earth's surface and seeps up naturally into land or water. Often, it is trapped beneath the surface by impermeable layers or rock structures. Within the crust, oil or gas deposits build up and form reservoirs. Reservoirs are like vast sponges filled with oil and gas. They can be as large as a city.
Planet Earth. If you look closer, you will see that whole other world exists beneath the surface of land and sea. Kilometers under the rocks, you will find deposits of oil and deposits of gas. They are the world's two most important sources of energy because they make the world go round, day in and day out. So, how do you find something that it is completely hidden beneath the Earth's surface? It is a mystery that people of the oil and gas industry are trying to solve, and for very good reasons. Drilling for hydrocarbons is expensive, and before they spend money on equipment and tools, exploration and production companies must have a reliable strategy that tells them where to drill. Geoscientists have a secret weapon called seismic exploration. It consists on sending acoustic energy beneath the ground to take a sound picture beneath the surface. When you want to know if oil and gas deposits are in a particular area, geophysical companies bring large trucks that have big vibrators on them. Most of the time, this is what generates the acoustic energy or a vibration. They use geophones or very sensitive seismic microphones to hear the reflected sounds. They set many geophones on the ground in a line, and they are attached to a recorder inside another truck. The vibrators send thousands of wavelets down into all different layers of the Earth. Some of these wavelets bounce off for the boundaries between the rocks below the surface and are reflected back to the geophones that are waiting to record them. Each geophone along the cable sends the received wavelets to a recording truck, where they are recorded and stored. Are wavelets reaching to the subsurface of the ocean. That's offshore seismic, and it requires a different device to send out the wavelets and record those that are reflected back. Out at sea, a seismic crew works on a vessel with a specially designed back so it's easier to lay floating cables or streamers, and all along linked to the streamers, microphones called hydrophones are attached one after another. Several of these hydrophones streamers are pulled behind the vessel at once. Acoustic sources are tooled behind the vessel in front of the streamers and release compressed air which creates the wavelets. These wavelets travel through the water and into the subsurface below, where, just like on land, they bounce off the rocks layers and then return to the hydrophones to be recorded. Here is what a seismic graph looks like after it has been recorded. Basically, it's a bunch of squiggles. There are still a few more steps to go before it begins to look like an actual picture of the Earth's interior. Right now, the data is still in its raw form. To get a picture that actually looks like the Earth beneath us, the data has to be processed. It takes a large supercomputing PC cluster to process the seismic data. This computer goes through all the different traces made by the wavelets and filters out everything we don't need, such as vibrations made by a tractor in a field nearby. Using really amazing computer applications and working on the state-of-the-art workstations, geoscientists could see the seismic data translated into a 3D picture. You might be thinking that there can be seen oil and gas, but believe it or not, geoscientists can look at this process daily with their trained eyes and make an informed decision about whether or not oil and gas deposits are in geological structures. Seismic data leads to a high percentage of drilling success. We will now see extraction and uses of oil, and then the same for gas.
Before the oil can be extracted from the reservoir, a well must firstly drill. This well is created during the second stage of petroleum industry, drilling. In order to carry out drilling operations, a temporary drilling rig is constructed. The large derrick allows for a pulley system that supports a long drill pipe attached to the drill babe. In the center, a turntable turns the Kelly, which is attached to the drill pipe as for allow drilling. As the driller goes deep underground, water is poured through it as for to wash the rock cuttings out. The resulting mud returns to the surface and passes through the shale shaker, which removes any unwanted solids. The mud is then poured into a tank, where drilling fluid is used to remove further rock cuttings. Once the well has been drilled to sufficient depth, the rig is deconstructed. The next stage of the petroleum industry is production. In this stage, the oil is extracted from the reservoir. This is done with an oil rig. In this process, a pump jack is used. A motor turns two crank rods aided by counterweights, which are attached to an arm which is also attached to one end, which is known as a walking beam. The beam is set in a pivot point and it rotates back and forth. Attached to the opposite end of the walking beam is the horse head, and attached to it is the bridle. As the head travels up and down with the movement of the walking beam, it pulls on the bridle, which is attached to a polish rod. The rod is attached to another rod known as a sucker rod, which extends all the way down to the oil reservoir. At the end of the sucker rod there are two valves. These valves pump up the oil from the ground into the surface as they move up and down with the momentum of the sucker rod. Once the oil is drawn to the surface, it then travels through a small pipe to a collection plant. This is the end of the third process, extraction. Then the oil must be sent from the collection plant to a refinery. The fourth stage of the petroleum industry is transportation. In this stage, the petroleum is transported from the production site. This can be done in several ways, by road, rail, sea, or pipeline. Pipelines can be thousands of meters long, and they are usually made of steel. The oil is kept in constant motion by regular pump stations along the pipeline and flow at 6 meters per second. The oil's final destination is the refinery, where the last stage of the petroleum industry takes place. The last stage of petroleum industry is the refinery. The petroleum, in its natural state, is almost useless, but its various components make it valuable and useful. These components all have different molecular weights and therefore different boiling points. Petroleum companies take advantage of these different boiling points and use it in order to separate the different components. In order to do this, the petroleum is burst heated up to temperatures of 600 degrees Celsius. The resulting petroleum gas is then piped into what is known as fractioning tower. As the gas rises up through the tower, different components condense at different heights. A series of bubble caps then prevent the oiling from falling after it is condensed. The petroleum is then pumped out through the pipes for further refining, such as the removal of sulfur. The major products resulting from petroleum refining are liquid petroleum gas, gasoline, naphtha, diesel fuels, fuel oil, lubricating oils, and petroleum coke.
Large hydrocarbons have high boiling points and so are removed at the bottom of the fractionating column. Smaller molecules are condensed higher up the column. We will now take a look at some of the common fractions as we move down from the top of the fractionating column. Some of the smallest molecules are between 1 and 4 carbons in length. This fraction has such a low boiling point that it is still as gas when it is removed from the very top of the fractionating column. This fraction is known as refinery gas or bottle gas. Bottle gas because it can be stored in bottles under high pressure. You could well have seen bottles of propane or butane running barbecues or heaters in your home, and these are examples of the refinery gas fraction. Petrol is between 5 to 7 carbons in length. It is still a fraction of small chain hydrocarbons, and therefore these vaporize at a low temperature and are easily ignited. This makes it useful as a fuel in the internal combustion engine of a car. Naphtha is not such a useful fuel, but it's a valuable source of organic molecules, which can be cracked to make more polymers made plastics, which are used in our everyday lives. Kerosene has an important use as a fuel for jet engines in aircraft and even in some rockets. Kerosene is also called paraffin in some parts of the world and is a common fuel burned in paraffin or kerosene lamps used for lighting. Diesel is the next fraction. It's a common fuel in cars, vans, and lorries. It is not as volatile as petrol, and instead of spark ignition like petrol, it ignites under compression. Below diesel are the residue fractions. Fuel oil as a fuel in power stations and ships, lubricating oil which sticks to surface and reduces frictions and protects from rust. And finally, waxes which along with the other oils can be used for polishing surface. The very bottom of fraction is bitumen. This is a thick black adhesive used on roads, either as a surface finish or combined with some stone chippings to create a solid resistant material. It can also be used to cover roofs due to its waterproofing properties. All these fractions are separated from the crude oil mixture. To try to explain the importance of crude oil, consider this. There is estimated to be over 1 billion cars in the world, of which many will use petroleum as fuel. There are many million flights per year, each burning kerosene fuel. Not forgetting the mass of plastic that is made each day for products and their packaging. And even the bitumen used to surface and resurface roads around the world.
For the extraction of gas, a hole is drilled, and a steel conductor casing is set to stabilize the ground at the top. When drilling begins, a solution of fresh water and clay, known as drilling mud, is pumped. This cools the drill, removes cutting, maintains proper pressure, and creates a boundary between the well and the rock formations. Drilling continues below the base of usable water to a depth specified by regulators based on local geology. The drill pipe is removed and more steel casing is inserted into the conductor casing. Cement is pumped into the casing out the bottom and back up to the surface, creating a sealed cement reinforced container that extends from the surface to below underground sources of drinking water. The surface casing also serves as the foundation for the blowout preventer, a key safety device. To ensure sufficient seal, the casing is pressure tested and then drilling resumes down to a kick-off point, where a specialized drilling motor is attached, allowing us to drill the curve and horizontal sections of the well. Typically, we are thousands of feet under usable water at a depth of approximately 10,000 to 13,000 feet, the equivalent of up to 9 Empire State Buildings. Multiple layers of rocks, of imperial metal rocks, separate the target formation from freshwater aquifers, preventing upward migration of natural gas and fracturing fluids into the groundwaters. Once the target is reached, the drilling assembly is removed and additional steel casing is inserted. More cement is pumped into the casing, out the bottom, and back up to a depth specified by regulators. This creates another cement reinforced container for the collection of gas. With a perforating tool, holes are shot in the casing and into the shale at the desired location. The hydraulic fracturing process, safely used for more than 60 years, is in over a million wells, now begins. A fluid consisting of water, sand, and a small amount of chemicals is pressurized and injected into the well, which penetrates the shale, fracturing the rock. Many of the chemicals used in the fracturation process are found in common household items and even in food products. Sand and ceramic particles, called propants, are carried by the fluid and deposited in the narrow gaps into the rock propping, opening the fractions so gas can flow into the well. To isolate the fracture zones, a plug is set inside the casing behind the perforated section and the process is repeated multiple times. The plugs are drilled out, allowing the gas and fluids to flow into the wellbore, where they can flow to the surface. The entire drilling and completion process generally takes only 2 to 3 months, compared to the 20 to 30-year productive life of a typical well. At the surface, the gas is separated from the fluids. The remaining water is diverted into storage tanks and then typically transported for disposal in government approved and regulated injection wells.